Welcome to Lesson 4, the one nobody wants to learn at 3 a.m., but everybody eventually does. Every pod, service, secret, every deployment in your cluster lives in etcd, and if you lose etcd, you don't just lose data, you lose Kubernetes itself. Tesla learned this in 2018, spending 2 days clawing back from a nearly stale backup. So today we're building the reflex, Raft, backups, restore drills, and the performance pitfalls that paid you. By the end, you'll have a tested answer to one question. How do we recover if etcd dies right now? The whole lesson hangs on 4 moves, and they map cleanly to the SRE loop. Observe, understand Raft, and why your cluster is 3 nodes or 5, never 4. Diagnose, the 30-second health check that tells you if etcd is actually healthy or just answering the phone. Act, snapshot, restore, defrag, the muscle memory that gets you back online in under 10 minutes. And document, the runbook that means 3 a.m. you doesn't have to think, only execute. Start with observe, and that means Raft. Every etcd node plays one of 3 roles, leader, follower, or briefly a candidate during an election, and writes only commit when a majority agrees. That's why cluster size matters. 3 nodes tolerate 1 failure, 5 tolerate 2, but 4 tolerates the same one as 3 while costing you an extra machine. Even numbers buy nothing, which is why you run 3 or 5 and never, ever 4. Lose quorum and the cluster freezes. AP server hangs, kubectl times out, and you're already behind. Now act, and the most important act you'll ever automate is the backup. 4 steps, no shortcuts. Snapshot with etcd-ctl, verify the hash and revision so you know the file isn't corrupt, ship it off the master to S3 or equivalent and encrypt it, then schedule it nightly with an alert that screams when it fails silently. A backup sitting on the same machine as etcd isn't a backup. It's wishful thinking that dies with the disk. So the backup exists. Now the real test. etcd is gone, the cluster is dark, and you have one job. Bring it back. 6 steps in this exact order. Stop the API server by moving its static pod manifest out of the manifests directory. Kubernetes notices within seconds and shuts it down. Same trick for etcd itself. Then restore the snapshot into a fresh data directory, never the original. Point the etcd manifest at that new directory, move both manifests back, and watch Kubernetes rebuild the control plane. 8 minutes, start to finish, if you've practiced. Restore is the dramatic save. But most of your etcd pain won't be drama. It'll be slow, and slow etcd means slow AP server, which means a slow cluster. 3 patterns explain almost everything. 1. Compaction. Every write creates a revision and old revisions pile up. Kubernetes auto-compacts every 5 minutes, but verify it. 2. Defragmentation reclaims that space, but it blocks writes, so run it on followers first, leader last, monthly, off-peak. 3. Disk. Run etcd-ctl check perf and demand 99th percentile f-sync under 10 milliseconds. Miss that target and you get leader elections, RPC timeouts, instability. Which is why production etcd lives on dedicated NVMe, off-the-worker nodes, with real resource limits. Non-negotiable. Now you know what hurts, so let's wire up the alarms before it happens. etcd ships about 80 Prometheus metrics, but 5 of them catch roughly 95% of real incidents. No leader? That's a P1 page. Your cluster is red only. Leader flapping more than 3 times in 10 minutes means disk, network, or resource starvation. F-sync, P99 over 100 milliseconds, etcd is suffocating. DB size near the 2 gig quota, defrag and check compaction. And if your last successful backup is older than 24 hours, your disaster recovery plan is fiction. Configure these today, not the night you need them. Alarms tell you when something breaks. These 6 reflexes keep it from breaking in the first place. Daily encrypted backups shipped off-site, endpoint status as your first command on any unfamiliar cluster, and the Raft math that says odd numbers only, 3 for most, 5 for critical, 7 only if you're spanning continents. Then dedicate the disk so fsync isn't fighting your workloads, defrag quarterly to actually reclaim space after compaction, and rehearse the restore on a kind cluster every quarter. A snapshot you've never restored isn't a backup. It's a hope. Pin this one. 12 patterns covering everything we've walked through. Health, status, and member list to observe, snapshot, save, status, and restore for your disaster recovery loop. Defrag, compact, and check perf for ongoing hygiene. And the 3 rules you never break. Quorum is n over 2 plus 1, always an odd number of members, always a dedicated SSD. If you remember nothing else from this lesson, remember this grid. Now the 5 mistakes that show up in real postmortems. Even-numbered clusters waste money and buy you nothing. Raft needs an odd n, always 3 or 5. Backups on the master die with the master, so ship them off cluster and encrypt them. A backup you've never restored isn't a backup, it's a hope. Drill it quarterly. Sharing disk with workloads turns fsync spikes into leader elections. And the 2 GB default quota will freeze your cluster the moment you stop watching it. Alert at 1.7, defrag on a schedule, and none of these will be the call that wakes you up. Reading about etcd won't save you at 3 a.m. Only your hands will. So 3 exercises in order. First, take a real snapshot on your kind cluster and verify it with snapshot status, because a corrupt backup can save successfully and still be unrestorable. Second, stop 2 of 3 control plane nodes and watch the API server hang. Bring 1 back and feel quorum return. Third, the resume grade drill. Snapshot, destroy the cluster, rebuild, and walk the full 6-step restore. First try takes 30 minutes. Third try, 8. That's the confidence that gets you trusted with prod. And that's lesson 4. You've got quorum math, snapshot save, the restore drill, and the perf knobs that keep fsync honest. The 4 things that turn etcd from a black box into something you can actually defend at 3 a.m. Tomorrow we go up the stack to networking, Calico, Cilium, Flannel, Iptables versus IPVS, and how a packet really finds its way from one pod to another. Get the drill done tonight. See you in lesson 5.